You're ready to go.
Yeah. Let me just do that. Which computer is that one?
You're on.
Sorry, we know we're trying to fix the in-screen display. Okay, so it's my pleasure to introduce our invited speaker, Abhishek Jain. Quick thing about him, he graduated from UCLA, supervised by Raphael Strasky and Amit Sahai, postdoc at MIT, and now he's been a faculty at JHU for several years now. Recently got tenure. And more importantly now is kind of the point of why we invited Abhishek. And, I think in general, one very good way to use these invited talks is to grab people who are doing really special research at hopefully at the late, this is kind of like a late early stage or early mid-career researcher. And if you looked at Abhishek recently, he's doing really well. First, we could do kind of superficial glance, and you see like a bunch of papers at Eurocrypt, crypto, stuff like that. Also advising students who are, doing really well also. But then if we take a little bit of a deeper look into it, for example, I think the work he might cover today, he recently had the solution to this open problem of getting non-interactive zero-knowledge proofs from the decisional Diffie-Hellman problem. And this was a really core open problem. I know, yeah, we're solving open problems all the time, but this is an open problem that if you just say it, people know what it is and have thought about it before. And when you kind of look into the techniques, you see there's this interactive protocol. There's a bunch of, well, he'll tell you better himself, but a bunch of guessing and all this, and you can understand it. But what's kind of hard to understand is like how he came up with it. So maybe we'll get some insights into a pretty amazing result there. So let's think. All
right, thanks, Brent. Okay, so today's talk will be about non-interactive proofs, and I'm borrowing the subtitle from Yuval from a couple of years ago talk. Okay, so broadly speaking, in this talk, I want to talk about non-interactive proofs, where there is a prover and there is a verifier, and the prover wants to prove some statement X in the language L to the verifier, and the prover wants to accomplish this by sending a single message to the verifier, and the verifier, upon receiving this message, either accepts or rejects the proof. So for these proofs to be useful, we typically require at least two properties. So the first is completeness, which says that if the proof is generated honestly and the verifier is honest, then proofs for true statements will be accepted. And the second property is soundness, which roughly says that if the statement is false, then no matter what the cheating prover does, the verifier will reject. So even with these two properties, non-interactive proofs on their own are kind of easy to achieve, if at least we talk about NP languages, because the proof could simply be the witness. So typically we associate some additional properties with non-interactive proofs. And the two properties that I am going to focus on in this talk are the following. So the first one is zero-knowledge property, introduced by Goldwasser, Micali, and Rakoff in the 80s in the interactive setting, and then subsequently ported to the non-interactive setting, which roughly says that the proof does not reveal anything beyond the validity of the statement. And this is going to be the primary focus of this talk, but I will also talk in some part about a second property, which is succinctness, or in short referred to as SNOGs, which is succinct non-interactive arguments. This was introduced in the interactive setting by Killian and then ported to the non-interactive setting by Micali and a lot of follow-up works, which roughly says that the communication and the verification complexity of the proof should be quite low, even smaller than the witness size. Okay, so why do we care about these properties? So first of all, hopefully for this audience, I don't need to convince you that these are really fascinating properties, both individually and together. So if cryptography is a study of seemingly paradoxical notions, then perhaps these two are very, very good representatives of that idea. Both of these properties give a lot of opportunities for flexing our theory muscles. And you can see an excellent talk by Yuval at Simons, which elaborates on this idea. Fortunately, there are also lots of applications of both of these properties that we have looked at in cryptography for many years. Most recently, these properties have probably been most popularized by the advent of blockchains. And perhaps mostly because of the last application, now these properties are really mainstream. You can find dedicated podcasts, blog posts about these notions, even by non-academics. You can find websites dedicated to studying zero knowledge that are maintained by non-academicians. There are standardization efforts for zero knowledge, and perhaps it might not be an overstatement to say that zero knowledge might even overtake Apache in popularity. Okay, so in this talk, I will talk about the history of these notions, but mostly focusing on the present in true mindfulness spirit. So even in the present, I will focus mostly on the topic of assumptions, namely what assumptions are really necessary for these properties, both for zero knowledge and succinctness. And time permitting, towards the end, I will talk maybe a little bit about theory versus practice for these properties. At least for the latter property, you can see excellent talks by Jens and Sarah at last Crypto and Eurocrypt. And towards the very end, I might touch upon a little bit about the trust models involved in these properties. Okay, so let me get started. So the first part of this talk will primarily focus on non-interactive zero knowledge proofs. This is going to be the longest part of this talk and perhaps the most technically intensive. The second part will be a little bit about succinct non-interactive arguments, a shorter part, and the final part will be the smallest, a little bit of discussion on both of these topics. Okay, any questions so far? Okay, let me then get started. So let's start with non-interactive zero knowledge proofs. So first and foremost, the notion as I defined earlier is actually impossible in the plain model. So typically we have to allow for some trusted setup, and the most common trusted setup that we talk about is common reference string setup, where there is some let's say trusted party that samples reference string, ideally a random string, and sends it to both the parties. The prover generates its proof using this reference string, and the verifier uses this reference string to verify the proof. This is perhaps the most commonly used model in theory, but also we often consider the random oracle model, and I'll talk about the differences in these two models shortly. But for the primary purposes of this talk, I'm going to focus on the common reference string model. Okay, so the main question that I'm interested in is what assumptions are necessary and sufficient for constructing non-interactive zero knowledge. So let me start with what we don't know about this even now. So even though non-interactive zero knowledge was introduced in the 80s, it's perhaps surprising that we still don't quite know its cryptographic complexity fairly well. So we don't quite know whether we can build NISICs from many crypt assumptions. If we make some relaxations, then we do know the answer. So for example, if we do allow interaction, then we know from many years ago that we can build NISICs interactive zero knowledge in Minicrypt, or if we allow random oracle. Perhaps even more surprisingly, we don't even understand very well the relationship between non-interactive zero knowledge and public key encryption. And as far as I know, no implication is known in either direction, except if you make a bunch of restrictions. So let's say you consider the designated verifier setting, and even there, if you only consider non-reusable designated verifier NISICs, then maybe we know some things, but not otherwise. And it should be fairly easy to see that this question also has implications to CPA versus CCA security in public encryption. Okay, so this is what we don't know, but here is what we know. So we do know, starting from the work of Bloom et al. And then Feigl-Lapidot-Shamir in the 80s and early 90s, we can build NISIX from a variety of assumptions. So we can build it from factoring related assumptions. We can build it from various standard assumptions on bilinear maps. This was pretty much the state of affairs until mid 2010s. And then in the last few years, a new sort of renewed focus started on building non-interactive zero knowledge, which led to constructions from learning with errors, and then even more recently from learning parity with noise, and other standard assumptions like DDH, QR, etc. Okay, so this was sort of the state of affairs until 2020, and if you look at this, you'll see that this perhaps looks much worse, or at least noticeably worse than public key encryption. And in fact, even worse than identity-based encryption, right? And in particular, the notable omission from this list of assumptions here, which are sufficient for NISIX, is assumptions related to the hardness of discrete log, right? So for example, GDH, we didn't quite know how to build NISIX from that. So another way to think about why this question is interesting or important is perhaps in answering what is the relative power of standard groups versus groups that come equipped with pairings. So starting from the work of Bonnet and Franklin, we saw that pairing groups can actually help us achieve a lot in cryptography that we didn't know earlier. So for example, it led to constructions of identity-based encryption, even attribute-based encryptions, and many other amazing tools, as well as NISIX. But we didn't quite know how to accomplish those tasks in standard non-pairing groups. At least for the case of identity-based encryption, this gap was somewhat narrowed in the work of Dotling and Gerg a few years ago, but the same is wasn't still clear for other settings. And we can ask whether such gaps are sort of inherent. Okay, so for the case of NISIX, this is the first result that I want to talk about. This is joint work with my student, Shengxiong Jin. So we show that we can build NISIX for all of NP from the sub-exponential hardness of the decisional Diffie-Hellman assumption in standard non-pairing groups. Okay, so a couple of remarks. This is not a practical scheme, but it does help reduce, I would say, the gap between pairing and non-pairing groups a little bit further, although there are still many things we don't know how to do in standard groups that we do know from pairing groups. And as far as answering the question between NISIX and public key encryption, again, some progress, but no definitive answer yet. Okay, so let me then proceed to give some background about how we obtained this result. So let me just mention, first of all, that prior to 2017-ish, I would say, roughly speaking, NISIX and the CRS model were mainly limited to these two sort of approaches. The first is the hidden bit model approach of Feigl, Lapidot, and Shamir. And then there was this other approach which crucially relied on bilinear maps, proposed by Groth, Ostrowski, and Sahai, which was subsequently made practical in many settings by Groth and Sahai. On the other hand, when it comes to random oracle model, I guess the canonical, the most well-known approach is due to Fiat-Shamir, which basically starts from a Sigma protocol, or more generally any interactive proof, which is public coin in the verifier, and then collapses it to a non-interactive proof. And the idea is simple. We equip the prover and verify with a random oracle. And now, instead of computing the verifier's challenge at random via interaction, now we basically do it non-interactively by computing it as the output of the random oracle on the first prover message. Right? So here, the first message being alpha. And now the prover can just directly compute the answer to the challenge, gamma, and then send them all together. The verifier can, of course, check that the challenge was computed correctly. Okay, so I'm not going to argue why this gives soundness, but hopefully you can see that by using properties of random oracle, we can actually argue that this is sound and in fact also zero knowledge. Okay, so we can obviously ask the question that if we have this really nice approach for constructing NISIX via the random oracle, can we actually instantiate the random oracle with some special hash function family? And of course, this is a very broad question. Random oracles are not just used here for constructing NISIX. They have been used for many other cryptographic primitives, at least for efficient cryptographic primitives. So this is a rather broad question. But focusing on the question of non-interactive zero knowledge, this is sort of what we knew. So there were a bunch of negative answers. In the case of interactive arguments, it was shown that there do exist specific protocols that you cannot collapse by using any hash function family. And even in the case of proofs, there was some partial conditional lower bounds. But then a possible route towards a positive resolution was shown or suggested by the notion of correlation interactable hash functions. The notion was initially introduced for a somewhat different reason, but then a path forward was shown in the work of Highlevel, Myers, and Rakoff. And then this idea was somehow adopted more strongly in the last few years. And I'm going to now talk about how this was done in the last few years to build NISIX from a variety of assumptions. So let me first talk about what this primitive is. So what are correlation interactable hash functions? So this is a family of hash functions, keyed hash functions. K denotes the key here. And we say that family of keyed hash functions is correlation interactable for a function family F. Actually, let me say that in general, we define correlation interactability with respect to a relation family, but here I'm simplifying it and focusing on searchable relations and just represented by this function family. So the idea is as follows. We require that for any member of this function family, if we sample a key K at random, a key for this hash function, and then give it to the adversary, it should be hard for the adversary to come up with an input X such that the output of the hash function on this X actually collides with the output of the function F on the same X. Okay, so the probability of this should be very small. So this is the notion of correlation interactability. And now let's see how this can help us in instantiating the random oracle in the future mu paradigm. Okay, so again, we start with the Sigma protocol, and we do more or less the same as we did earlier when we were using random oracles, except that now we sample a key for this collision interactable hash function family, and that's now part of the CRS and known to both the parties. And now the prover works in the same manner as before, except that now he uses the hash function to actually compute the challenge beta. Okay, and the rest is as before. So we can ask, why does this actually work? Why does this give us a NISIX? So arguing zero knowledge is actually easy, so I'm not really going to talk about that. More or less can be argued by relying on the honest verifier zero knowledge property of the underlying Sigma protocol. But let me just focus on soundness, which is the more interesting case here. Okay, so let's first recall that Sigma protocols have this so-called special soundness property, which says that if you look at a proof for a false statement, right? So let's say we have a transcript alpha, beta, gamma. So it says that if I give you two transcripts, two accepting transcripts with the same prefix, so the same alpha, but different challenges, beta 0 and beta 1, and corresponding answers, then you can actually extract a witness. Okay, good. So this is a special soundness property. And now if we have this property, we can note that for any alpha, there exists actually a unique beta such that the transcript alpha, beta, gamma will be accepted, right? This is a consequence of the special soundness property. And now that we have this uniqueness guarantee, we can define a mapping, so-called function, which I'm calling a bad function, which maps alpha to this bad beta, right? This beta that would have resulted in an accepting transcript, even though the statement is false. Okay. So now Now let's argue someness given this observation. So let's say we use CIH as the hash function family for instantiating the random oracle, and we will use CIH, which is correlation intractable with respect to the family of bad functions. Okay. So now, if a transcript is accepted, then on the one hand, just the way we constructed the protocol, we have that beta is the output of the hash function, right? But at the same time, we also have that beta is equal to the output of the function bad, right? So what this means is that if you notice the right-hand side of the equality, we have that the output of the hash function on alpha is equal to the output of bad on alpha, right? So this is a contradiction to the correlation intractability property. Okay, so let me mention, since it's not cited here, all of this abstraction that I'm using here is from prior works, of course, and in particular, the abstraction that I'm using here is from the work of Kennedy et al., 2019, and even more so for this slide. So far, I haven't really talked about whether the bad function is efficiently computable or not. And we can actually make it efficiently computable by using trapdoor sigma protocols, which are basically sigma protocols in the CRS model, where the first message is alpha or of a particular form. They are commitments to some message. And the idea is that given the trapdoor for this commitment, if you think of the commitment as implemented using a public encryption scheme, then using the secret key, you can actually extract M, which helps you find the bad beta, and now you have an efficient function bad. Okay, so why does this matter? It helps because now you can obtain a contradiction by the same approach as earlier. For correlation intractable hash functions that are correlation intractable for efficiently computable functions, right? So smaller class, potentially smaller class of functions. So this makes the task of building CIH a little bit easier. Okay, so one thing to point out here is that this function bad here involves the decryption of the commitment, and this sort of affects, what is the complexity of this bad function, right? And this will matter later on. Okay, so now that we have this approach, we can ask what kind of CIH do we know, right? What class of functions do they support? And I'm going to restrict my attention to CIH constructions based on standard assumptions. So based on learning with errors assumption, we actually know CIH for all polynomial size circuits. This was shown in the work of Pikert and Sheehan, building on the work of Kennedy et al. Previously. And subsequently, it was extended to even a bigger class of relations. Most recently in the work of Holmgren and Lombardi and Rothblum. So using these results, in particular the first of these results, you can obtain NISX from the learning with error assumption, right? This was a breakthrough result a couple of years ago, and this was the route towards obtaining that result. On the other hand, things are somewhat more limited if we consider other assumptions. So if we consider other standard assumptions like DDH, QR, DCR, etc., the only other known approach for building CIH based on these assumptions was given last year in the work of Brakersky, Coppola, and Maurer, who showed how to build a CIH for constant degree polynomials. Okay. And this is a somewhat limited class, which is why they could build NISX using this route from essentially the same assumption, right? So you could take CIH for this family of functions and use it to build NISX from DDH or QR or DCR, but you additionally need the LPN assumption. Okay. And the use of LPN in their work was very much to allow for using this CIH family. Okay, so we can ask whether this route could actually give you directly a NISX from DDH, and it seems insufficient, mainly because the class of functions supported here is quite small. If you think about building NISX from DDH, and you think about the bad function that I mentioned earlier, because it involves decryption of the commitment, if you want to instantiate everything from DDH, it seems quite hard. We don't quite know how to build such things where the decryption would be captured by a constant degree polynomial, right? Okay, so the question we can ask is, for the purposes of constructing NISX, but even broadly, can we build CIH for larger class of functions from assumptions other than LWE? Okay. So going back to the application of NISX from DDH, what we show in the same work is you can build correlation interactable hash functions for constant depth threshold circuits, so TC0, from sub-exponential DDH. The result is slightly more general, but this is essentially the main result. And we show that this is actually sufficient for building NISX from sub-exponential DDH via the Fiat-Shamir plus CIH route. So TC0 is sufficient. And if you want a one-line intuition, it's essentially that Elgamal encryption ciphertext can actually be decrypted in TC0. Okay. If that seems somewhat unbelievable, the intuition then is that if you're familiar with now Rheingold PRFs and you know that they can be evaluated in TC0, it's essentially the same intuition here as well. Okay, so I'm not going to show why TC0 is sufficient. Okay, you can trust me that this is true. So then the main task is how can we build CIH for constant depth threshold circuits from DDH. Okay. Any questions so far? Carry on then. So the main tool that we use to build CIH for TC0 is a primitive that we call interactive trapdoor hashing. If the name sounds a mouthful, don't worry, I'll explain shortly why we use this nomenclature. So it's a protocol between two parties, sender and a receiver. And roughly speaking, you can think of it as a very, very special form of secure two-party computation protocol with lots of properties and lots of structure. So the sender has some input X, and the receiver has an input of function F with the multi-bit output. And the parties exchange messages with each other in an alternating fashion. And we want a bunch of properties from this protocol. So first of all, at the end of this protocol, the sender obtains some encoding, which we denote as E. This is something that the sender computes on its own. And then the receiver on its own computes a value D, which we call the decoding. Okay. And the first property we want is additive reconstruction. That is, by adding or XORing these two values, encoding and decoding, you can obtain the output of the function F on X. Okay, so if you're familiar with homomorphic secret sharing, this is very reminiscent of that. The second property, and this is really a key property of this notion, is that we want that the sender's communication is very small. It's laconic in the sense that the size of each of the messages that the sender sends is in fact even independent of the input and output length. It only depends, it's bounded by the security parameter. And this is a really, really strong property, right? Which is what gives this primitive a lot of power, as we'll see soon. And the third property is function hiding, which basically says that the messages of the receiver hide the function F. Okay, good. So this primitive is essentially, morally speaking, a generalization of the notion of trapdoor hash functions, which was introduced by Dortlinger, Ishai, Malavolta, Moore, and Ostrowski a couple of years ago. And there are some syntactic differences, but morally speaking, you can think of trapdoor hash functions as essentially two-round version of interactive trapdoor hashing. Again, there are some minor syntactic differences, but this is essentially the way to look at it. And interactive trapdoor hashing essentially says, okay, let's allow more interaction, right? But the rest of the properties are essentially the same. And trapdoor hash functions were originally introduced for constructing RAID-efficient cryptographic primitives like RAID-1 oblivious transfer, PIR, and so on. But then in 2020, Brzezinski, Coppola, and Moore actually showed that you can use this primitive to build correlation interactable hash functions. Okay, and this is where the focus on physics comes in. Okay, and again, the name of this primitive interactive trapdoor hashing is essentially coming from trapdoor hash functions. Okay, so now let's see why this primitive is useful for building correlation interactable hash functions. So the implication from trapdoor hash functions, so two-round version of interactive trapdoor hashing, two correlation interactable hash functions was actually shown by Brzezinski, Coppola, and Moore. And this was a general implication. The problem is that trapdoor hash functions are only known for a very small class of functions, namely constant degree polynomials. And again, if you look at the restrictions, all the properties that are required, maybe this is not so surprising that this is a hard to build primitive. And what we show is essentially a two-step approach. So first, as is often the case in in secure computation literature, if you allow more interaction, you can achieve more. And this is what we show, that if you allow for more interaction by generalizing the notion of trapdoor hash to interactive trapdoor hash, you can capture a bigger class of computations. So in fact, by just going to even arbitrary constant rounds, you can already do TC0. And now this may seem a little bit strange. Well, now that we have all this interaction, what do we do with it, right? How does it help us in building physics? So we show that you can actually do round compression. So you can actually take this constant round protocols and then compress it to build or collapse its round to build correlation interactable hash functions for the same family. It's important here in this transformation that the starting interactive trapdoor hash is constant round. Okay. Otherwise, the first step is actually quite general. If you allow for polynomial rounds, you can even go to p/poly. Okay. So I will mainly talk about the second part here, and the first part will be much briefer. So let's see, how do we do round compression? So this is the structure of interactive trapdoor hashing protocol, and we want to build CIH from it. So here is what we do. So the receiver, he simply imagines an execution of this protocol. So suppose I want to set the key for the hash function, right? That's my goal. I want to define a hash function. I want to define a key and then the hashing algorithm. So what we do is we just imagine an execution of this protocol. We imagine all the receiver messages, and then we collect them together and put them as part of the key, where the key additionally contains a random pad, a random string u, okay, which is, let's say, n bits, where n is larger than the security parameter. Okay. Now, of course, this seems a little bit strange, right? How can we imagine the messages of the receiver without thinking about the sender messages, right? The receiver messages depend upon the sender messages. So we simply guess them. Okay, so we guess the sender's messages while generating this key. Okay, and now to evaluate the hash function, the sender will take the input x, right, on which he wants to evaluate the hash, and then in his mind he will just run an execution of this interactive trapdoor hashing protocol. So for the first round, it will take the first part of the key and treat it as the receiver's message, then compute its next message, and then take the second part of the key, treat it as the second receiver message, and so on. At the end, it will obtain this encoding E. And now the final output of the hash will be this encoding E XORed with this random pad U. Okay. Okay, so now we want to show that this construction is actually correlation interactable. So this is the definition of correlation interactability again. And we want to show that this construction here in the small box, where K is the key, actually achieves correlation interactability. Okay, so here is how we do it. So first, I'll show you why this is true for the case of 2 rounds. And this is essentially the proof from Brzezinski, Coppola, and Moore. So in the 2-round case, the receiver has only one message, the sender has only one message, right? Okay. So now, first of all, from the correctness of the trapdoor hashing, right? We have that the output of the function f on x is equal to the XOR of the encoding and the decoding. And now let's say that this construction is not correlation interactable. So then on the left-hand side, we have that the adversary actually managed to obtain an x such that h of x is equal to f of x, right, with high probability. Okay, so now on the right-hand side, we can just cancel out the encodings, right, in the two equations. And now we get that the decoding D is actually equal to the pad, the random pad U. Okay, and remember that the random pad U is n bits long, which is potentially much longer than the security parameter lambda. Okay, so in particular, the decoding D actually has a pretty sparse range because it only depends on the message, this very small message that the sender sent, right? So its space is quite sparse, whereas U actually is n bits long. So therefore, we can argue that the probability that D is actually equals U, adversary actually managed to find an X such that this holds is very small. It is negligible. So this is essentially the proof for the 2-round case. And now let's try to generalize it to more than 2 rounds. So let's say 4 rounds. Okay, so now there are 2 receiver messages and there are 2 sender messages. Okay, so again, recall that the way we constructed the key was by guessing the sender message, right? So first of all, the additive reconstruction property now will only hold up to the probability that our guess is actually correct, right? We made a guess about the sender message. And now if the sender actually happened to choose an X, which results in the same small message, then we have additive reconstruction correctness. Okay, but of course, this guess will only be correct with some small probability, right? Roughly 2 to the minus lambda. So can we still prove correlation intractability? So here is an oversimplified argument why we can still argue. So note that our guess is correct with probability 2 to the minus lambda, right? And again, I'm cheating a little bit here, but let's say this is the case. Then from guessing correctness, we have that D actually matches the random pad U with probability still at least 2 to the minus lambda, right? So it's not too small. It's small, but not too small. But from the same argument as before, from the sparsity of D, right, the decoding value, we have that it's the probability of D matching U is actually upper bounded by 2 to the minus omega n, right? So it's very small. So when n is substantially larger than lambda, then we get a contradiction, right? The left-hand side is smaller than the right-hand side, which is, yeah. So you get a contradiction. Okay, so I was cheating a little bit here because here I sort of assumed that the adversary cannot infer any information about our guesses by looking at the key, the hash key, but that's not quite true, right? The correlation intractability game is adaptive in the sense that the adversary sees the key and then has to come up with an X. And in our case, the key actually encodes some information about our guesses, right? How? Well, we can say that the receiver messages hide information about the guesses, but it's not they don't hide it perfectly, right? The function hiding property is only computational. Okay, so in particular, the function hiding property says that if I look at any receiver message, which depends on the state of the receiver, here the state actually depends on the prior sender messages, then it's computationally indistinguishable from a randomly sampled string. So we have only computational function hiding, so we still need to make the previous argument work, and we can do it by by basically strengthening the function hiding property. Now it's going to be sub-exponential function hiding, and we can play with the security parameters carefully. So we can make the security parameter for the first round, let's say some lambda 1. For the second round, we can make it slightly bigger, lambda 2, where lambda 2 is bigger than lambda 1, and so on, right? And the structure of our protocol allows for playing with the security parameters in this manner, right? For each round, we can actually pick a different security parameter. And now the idea is that if you look at the probability of the guess, the sender's message guess that we made being correct, it's essentially the same as before, 2 to the minus lambda 1, but we lose a little bit here because of the function hiding property, right? But how much do we lose? We lose essentially 2 to the minus lambda 2 to the C, where C is some constant, right? So we lose a little bit, but not too much by playing with the security parameters. So the first part is again coming from the random case, and the second loss is because of the sub-exponential function hiding property. So now you can make this idea, more general. You can extend it to constant rounds or even log-log rounds, and more or less the same proof as earlier works, just that you have to take into account the loss due to function hiding. But otherwise, the same idea as before works. Okay, so that's essentially why we can build correlation interactable hash functions from interactive trapdoor hashing. Okay. So now let me just give you a very, very short overview of why more interaction can help us in expanding the class of computations that we can achieve by interactive trapdoor hashing. Okay, so the approach is very standard. How we work in secure computation protocols. Let's compute layer by layer, right? And this is essentially what we will do here as well. We take a TC0 circuit, layerize it, and now we will evaluate it layer by layer. So for the first layer, we will come up with an interactive trapdoor hashing protocol and use it to evaluate the first layer of gates and then second layer of gates, and then just compose them together so that we get interactive trapdoor hashing for TC0 circuits. One thing that I'm going to remark is that interactive trapdoor hashing does not give you the output as it is, right? It gives you it in a secret sharing form. So we need to XOR those values to proceed to the next layer of computation. And this XORing or shares can be absorbed essentially in the functionality of the next layer. So I'm not going to mention it. So now let's just talk about one layer, which consists of threshold gates, or rather XOR then threshold gates. Okay, and let's just think about a single gate. So what we do is, in principle, we decompose this computation into two different linear functions. And then we have trapdoor hash functions. We already know trapdoor hash functions for linear functions. So we can evaluate each of these functions via such a trapdoor hash function. And then we put them together and we get interactive trapdoor hashing for a threshold gate. Okay, so now if you're paying attention, you'll see that I just pulled off a magic trick, right? So what I did is I took a threshold gate, or rather an XOR then threshold gate, which involves nonlinear computation, and I decomposed it into two linear functions, right? So that doesn't sound quite right? If I could do that, I could just put these two linear functions together and I could do it non-interactively, right? So where is the interaction? So the crucial use of interaction is in how we actually obtain the description of these linear functions. So the main point is that we require the sender and the receiver to do some nonlinear processing, which is intermediate, and it's outside the protocol, and that helps them obtain the description of the second linear function, and then they can continue, right? So this is how we decompose this computation into two simple functions. And this is all I want to say about this construction. The details on what are the two linear functions and so on, you can find them in the paper or in a separate talk by Shengzhong. The details here are not that complicated. Okay. So that was all I wanted to talk about the current state of affairs in non-interactive zero knowledge. Let me now proceed to the second part of the talk. We'll talk a little bit about succinct non-interactive arguments. Okay, so succinct non-interactive arguments, or SNARKs in short, essentially the same setting as before, where the prover wants to prove some statement to the verifier. Here I've taken a Turing machine model of representation, and he wants to convince the verifier of the statement via a non-interactive proof. The key requirement here is that the verification time, both the proof size and the verification time, is quite small, smaller than the time to run the machine. And as in the case of non-interactive zero knowledge, this notion is also impossible to achieve in the plain model. Here, the impossibility comes, if you're talking about non-uniform provers. So again, typically we either supplement the model with a CRS or random ortho to bypass the impossibility results. And just like the case of NISX, the main question that I'm interested in here is what assumptions can we use to build SNARKs? Okay. in particular snarks for NP. So here is the state of affairs. We can build snarks for NP if we allow for either the random oracle model or knowledge type assumptions, right? Assumptions that involve extractability. This is a very long line of work, starting from the work of Mikhaili, and then very impressive sequence of works. In fact, very productive line of research, which is very active presently. And I should mention that many of the more recent schemes have been implemented, and some of them are actually used in practice. This is in fact, responsible for many new startups in the blockchain area. Okay, so this is the side of result that involves either random oracle or some non-standard assumptions. And unfortunately, there is a barrier for building snarks for NP from standard assumptions. And this is the beautiful work of Gentry Wicks. I should mention that there are some caveats here, but I'll put them aside for now, maybe mention them at the end. So given this lower bound of Gentry Wicks, we can ask whether we can build snarks for subclasses of NP while still relying on standard assumptions. So the main subclass that I want to mention is snarks for P. So deterministic polynomial time computation, same setting as before, except that now the client is asking the prover to perform some deterministic polynomial time computation and prove that it did so correctly. So obviously, this is a natural and important subclass of NP, but which is independently interesting, but also has some useful cryptographic applications directly. So we know that using NISX and FHE, we can build shorter NISX, where the size of the NISX doesn't depend on the relation size, only on the witness size. And now using snarks for P, you can transfer this property also to the verification time. You can also use snarks for P together with suitable sequential functions to build verifiable delay functions. Okay. So prior work in this regime is roughly in two categories. So first category, which is also a very productive line of research, starting from the work of Pillai, Raz, and Rodblum. So it restricts the setting by allowing the verifier to hold a secret key and use that for verification. So this is the designated verifier setting. And here we can actually do, we can actually achieve snarks for P and even some other subclasses of NP by relying on standard assumptions. But if we insist on public verification, where the proof can be verified by anyone, then again, until a year ago, what we knew was how to build such proofs from either obfuscation style assumptions or some new but non-standard assumptions on bilinear maps. So the question we can ask is whether we can build snarks for P from standard assumptions. And some really nice progress was made in this direction last year by Javale et al., who showed that if you restrict the computation to bounded depth, then you can actually achieve snarks for such circuits from sub-exponential LWE. And the result improved upon a prior work of Canetti et al. That used stronger assumptions. Okay, so before even talking about how, whether we can resolve this question or not, let's actually see what are the intuitive barriers towards resolving this question. So in the spirit of using Fiat-Shamir with correlation interactability, we can ask whether we can round collapse succinct interactive protocols, right? Earlier, we were looking at arbitrary public coin interactive proofs. Now we can say, well, can we start from a protocol which is succinct and then apply the CIH transformation on it? So the canonical example of such a protocol would be Killian. But there are some barriers to it, which was shown a couple of years ago by Bartusek et al. Morally speaking, the results said that instantiating random oracle in this, in Killian is going to be hard. Okay, the result is more nuanced. But perhaps a high-level point is that Killian is an argument system, so it's computationally sound, whereas the standard methodology of using the correlation interactability seems to require starting from protocols that are statistically sound, or rather proofs. Okay, and sort of a one-line argument for why this is true is that we start from a protocol and define some bad relation on it, and then the soundness of the non-interactive protocol requires CIH for that bad relation, right? But morally speaking, the best results we know and maybe perhaps even hope for is CIH for sparse relations. That is where for any alpha, the fraction of beta which leads to accept is negligible. And this means that essentially now we must start from a protocol which is statistically sound, right? If we are saying that for any alpha, then the fraction of beta that leads to accept is negligible. In the case of arguments, that may not be true, right? It may be much larger fraction. Okay, so now we can ask, well, why not start with interactive proofs then, right? So indeed, this is the approach that was taken in the work of Jovalde et al. And previously Canetti et al., where they started from particular kind of interactive proofs, namely Goldwasser-Kalai-Rothblum's protocol for bounded depth computation, and did manage to collapse its rounds to build snarks for bounded depth computation. So there are some other special case succinct interactive proofs, but in general, if you want succinct interactive proofs for all of P, that seems unlikely. So this puts us in a bind. We want to use this nice framework for building snarks, but it seems like we don't have a good starting point. So nevertheless, in a joint work with my students, Arka Rai Chaudhary and Shengsheng Chin, earlier this year, we showed that we can build snarks for P from the learning with errors assumption. And in some sense, to kind of bypass the previous bind, what we do is we sort of shift the problem of computing snarks for P to a related problem, a related subclass of NP, which is batch NP. In batch NP, the idea is that the prover now wants to prove a bunch of statements, a batch of statements, let's say K, X1 to XK, all in the same language. And he wants to do it by using a single message. And here, the efficiency properties are as follows. We want that the communication complexity should be much smaller than sending all the witnesses, right? And accordingly, we can put restrictions on the verification time. So batch verification is, it's a pretty well-studied problem. It's been studied for signature schemes and other cryptographic primitives. So batch NP is a pretty useful subclass of NP on its own. Importantly, here the Gentry-Vicks lower bound doesn't hold. However, if we want to build snarks for batch NP, it seems like we have somewhat similar challenges as P. For example, we don't quite know interactive proofs, succinct interactive proofs for batch NP. Okay? We do know them for UP, for example, but it's not like there is a lower bound there, or that they're unlikely to exist. We just don't know. Okay. So what we do is we abstract out this notion of dual mode interactive arguments for batch NP, and this is sort of the key idea that lets us circumvent the barriers that I mentioned earlier. So what we do is we define interactive arguments for batch NP in sort of a two-mode setting. So these protocols are now going to be in the CRS model, and there will be a normal mode of the CRS. But then there will also be a trapdoor mode where the CRS can be programmed on some index, let's say I, where I varies from 1 to K. Okay? And the requirement is that once you switch the CRS to the trapdoor mode, then this protocol becomes statistically sound at index I, meaning that at index I, the cheating prover cannot prove any false statement, even if the prover is unbounded. Okay. So now in the trapdoor mode, we have a statistical soundness property, except that a particular index I, which is programmed in the CRS. Okay. And for those of you who are familiar with this notion of somewhere statistically binding commitments, you can see sort of the analog here. And in fact, the notion is inspired by that notion, by SSB commitments. Okay. So now sort of a one-page proof for why this helps in round collapse via CIH is So if you have an interactive argument where, let's say the tuple of statements, being in the language does not hold, it means that there is at least one index I, right, where xi is not in the language. So now, in order to do round compression, what we can do is we can switch the CRS to the trapdoor mode, right, where the trapdoor CRS is programmed at I. Right? You can guess I in advance, and it incurs a small loss, so that's not a problem. And now we get the guarantee that at index I, xi, that the proof must be statistically sound, right? And once we get statistical soundness, now we can actually, use correlation interactability as we were able to do before, right? So this is sort of what helps us bypass that conceptual barrier. And once you have SNARKs for batch and P, you can move to P. Again, I'm going to give you an extremely high level intuition for why you can do so. I'm going to cheat a lot. So let's say we take a P computation and we break it down into intermediate states, let's say ST1 to ST4 here, right? You can divide it into lots of steps. And now you can write down a bunch of batch statements. So the first statement will say that the first step of computation was correct. The second statement will say that the second step of computation was correct, and so on. And now I can say, well, let's just prove these batch of statements, right? So we can use a SNARK for batch and P for proving this. So let's say we just run it in the normal mode. Now what we can do is, we can switch the CRS into the trapdoor mode, right? And instead of programming it at one index, we can program it at two indices, right? Two adjacent indices. And we can argue that, let's say if we program it at 1, 2, then we can argue that the first step is correct, right? Then we can, by switching the CRS, we can argue that the second step is correct, and so on and so forth. So, from the beginning, we can go till the end and argue everything is correct. So that's sort of the high level principle. There are a bunch of things that I was hiding here and I was cheating. So first, of course, we have to compress everything, right? I mean, we cannot give out all these states in the clear. That would already be a lot of communication. So we can compress them by using SSB commitments. But perhaps the biggest challenge is that unlike batch arguments where the statements can be sort of independent, right? X1, X2, X3, they can be independent and they sort of don't have any bearing with each other. Here, they're related, right? And the problem is that when we switch the CRS every time to prove that either the first step was correct or the second step was correct, we have to ensure continuity and we have to ensure that the adversary did not change these states, these intermediate states, when we actually switch the CRS. So that's sort of the key challenge. And it's possible to circumvent that by using a notion of a stronger form of SSB commitments called no signaling commitments. You'll hear about them, I think, on Thursday, so I'm going to skip it here. Let me mention that an alternative transformation from SNARK for batch and P2P was actually shown by Kalai, Vakunnathan, and Zhang. And I think Rachel will talk about this later today. So, yeah. Okay. So this is why we can build SNARKs for batch and P, at least moderately speaking, and why they are useful for building SNARKs for P. We do show a construction of SNARKs for batch and P from LWE, but I'm not going to talk about it today. There is a talk by Zheng, which is online, which explains this in a lot of details, so I recommend you to watch that. Okay, so in the last maybe 5 minutes or fewer, let me have a short discussion about the current state of affairs and what kind of questions we would like to address going forward. So the first, perhaps most important question in this line of research is whether there are ways to circumvent Gentry-Wicks lower bound to build SNARKs for maybe NP or other important subclasses. So let me mention the caveats in the Gentry-Wicks lower bound, right? So first of all, the lower bound requires adaptive soundness. So it only rules out SNARKs for batch and P where the soundness is adaptive. Namely, the prover chooses the statement after looking at the CRS. So if you weaken the soundness requirement to a non-adaptive where the adversary must declare the statement in advance before then seeing the CRS, we don't know of any lower bound. Also, the lower bound is black box in nature. It uses the reduction uses the adversary in a black box way. So if you can develop non-black box techniques, maybe there would be a way to overcome that. So non-black box reductions are far and few in cryptography, but the first restriction seems somewhat more tempting to exploit. And strangely, or perhaps maybe somewhat surprisingly, we still don't know how to exploit it. And I should mention that, in fact, this is so far something that seems to be even outside the reach of IO, at least if we require short CRS. If you require long CRS, then indeed you can do things, but with short CRS, it seems hard. Of course, we can ask the question whether we can build snarks for other subclasses of NP from standard assumptions. And currently, we know for a few subclasses, but it's perhaps natural to ask if we can extend the current state of affairs to other interesting classes of NP. And again, the main challenge here usually seems to be how to ensure consistency across in the computation. We can also ask if we can come up with different models here, maybe change the model somehow. Maybe change the model of communication, some other relaxations. And I should say that, echoing Mihir here, perhaps the biggest success story of theoretical crypto is in coming up with new and interesting models. So maybe there are interesting things we could try here as well. Okay, so I think I'm already running out of time, but if it's okay, can I use 2 more minutes, Brent?
Sure.
Okay. All right. So I'm going to remark, in 2 slides about theory versus practice of these primitives, so NISICs and snarks. So if you look at the correlation interactability framework, you can say that perhaps what it helped us do is actually build a bridge from practice to theory, right? This is somewhat unconventional, going from practice to theory. But perhaps this is to be expected if we are able to instantiate random oracles in cryptographic primitives. One could argue that perhaps this bridge is somewhat one way, we go from practice to theory, but we don't know the way back here, at least the current state of affairs. So let me explain why. So let's talk about assumptions. So far, we know very few approaches for achieving correlation interactability. And these approaches seem to require compression and hiding. And we know how to achieve these properties. I'm being informal here, but we know how to achieve this using FHE or trapdoor hash, which is also very related to HSS. So we can ask if these techniques are necessary. Perhaps more to the point, we can ask if we can build CIH from weaker assumptions, maybe with information theoretically for at least small classes of functions. And there is some recent work, but the answer still remains unclear. Let me say that resolving this question would have some bearing on the public key encryption versus NISIC question, and perhaps also on the efficiency. If we manage to substantially reduce the assumptions, it's likely that we will also improve the efficiency of these constructions. Another point I want to mention is that the known constructions of CIH require the code of the relation or the function for which we require correlation interactability. So what this results is that if we use the trapdoor sigma protocol approach, where the relation is cryptographic in nature, we end up with sort of a non-black box use of cryptography in the overall construction. And we can ask if this is inherent. Okay, so I'm even more out of time, so I'm going to skip the last point of this talk, trust models. Okay, so let me summarize by saying that non-interactive proofs are really cool, and this is a good time to work on them. So thank you.
Okay, so we'll take questions from the audience. Also, Justin will let us know if some remote people chime in. Okay.
Well, I've got some questions. They showed up in the chat, or not the chat, but the question forum. So my first one was, doesn't the assumption of completeness imply inconsistency? is soundness a notion of restricted or bordered to an E epsilon consistency?
I'm not sure I understand the question. Possible to elaborate?
Well, you spoke of the soundness of the decision problem.
Mhm.
But in your first or second slide, you assumed completeness.
Mhm.
Under Gödel's theorem, doesn't the assumption of completeness imply inconsistency? And you emphasized at the end of your talk that the major problem was ensuring consistency.
So I think there might be some confusion here. So first of all, if you're referring to completeness, completeness is for true statements, soundness is for false statements. But if you're referring to consistency later on, that was that was an informal use of consistency, but it was really more about continuity in the computation, ensuring that when we look at each slice of the computation one at a time and argue about it, when we switch from one hybrid to the other, there's a continuity and the shared parts are consistent.
That's essentially important these days in quantum computing, isn't it? My second question was, isn't guessing the sender's key the same as brute force search?
It is. We are essentially, simply guessing there. But the point is that again, we can set up parameters appropriately so that we can still argue correlation interactability. Yeah.
And my third question was, once again today, are you assuming shared, trusted, quote, perfect time, unquote, amongst the interactive parties?
Typically, interactive protocols, we define them in the synchronous model. Yeah.
I think the assumption of...
Sorry, just to cut off, we have one question from the audience in place.
Okay.
Okay.
Yeah.
Sorry.
Oh, because
Repeat
D,
that if you will.
yeah, so the question was, why was the vector D sparse? So D only really depends on the sender's message, right? So the thing is that the sender's message is upper bounded by the security parameter, and the U is n bits long, which is much larger than lambda. So yeah, so I mean, yeah, there I was just talking about one round, but yeah, for every round it is, yeah. Any other questions?
That's kind of a meta question. Like, how long did it? There were a lot of moving parts. For example, like the guessing, and then the showing that things were in TC0. How long did it take? Honestly,
how long did it take? Well, I mean, I should anyway credit Zhengsheng for the key ideas. I would say that perhaps. I mean, we did, to be honest, we didn't even start with the question of constructing physics from DDH. We were trying to address a slightly different question, but eventually we realized that we could do it from DDH. But the key idea was really the interaction. Once you notice that interaction can actually help. I think the round collapsing part, the guessing and the round collapsing perhaps is something very natural.
Okay. So you thought, okay, if I have interaction, I can do this class, and then maybe if you get that far, then the guess.
Yeah. I mean, the thing is that if you try to use interaction, initially it seems counterintuitive, right? Like, why would I use interaction in this setting where my goal is to achieve non-interactivity, right? So it just seems sort of counterintuitive to use that. But yeah, once you sort of get over that point, just look at the question of CIH completely independently, right? Correlation interactability independently, then it perhaps makes more sense. Yeah. Shai, did you have a question? Yeah.
Just whether all the possibilities of collision have any bearing on this line, and there's all things that say that the length of things have to be at least that much.
I'm actually not very familiar with the whole lower bounds. Yeah, so I don't know if somebody else might volunteer to answer that question. Maybe Daniel. I don't know.
Not tried it.
Yeah. They must be over somehow bypassing them. I'm not sure how. Yeah.
Okay, well, that was a great talk, and let's thank him again.